Okay, let's make a start. 5:30. So, as I was kind of mentioning at the beginning, we are going to continue on with where we left off, Chapter 11 Review. So we're doing our Integration SAC preparation. We've done a decent number of the Practice SAC external response sections, so we've been moving on to the Cambridge Chapter Review to get another bunch of practice out of those. So let's continue on then. So, question 8. Let's see, just double checking all my screens are good. Yes, and yes, and yes. Okay. So, question 8a. If we have y equals the x natural log x, first up, find derivative, hence find a related integral. These are a very specific set of questions that follow the exact same procedure over and over again. I'll give you guys a moment to figure out what that might be and potentially suggest some starting points for us.
Would you use the product rule to find the derivative?
Yeah, product rule to find the derivative sounds about right for this, yes. So you've got x times natural log x, that's two functions that are multiplied together, hence we will be using the product rule for this. I have also noticed that this is a TeX active, so probably using the CAS where appropriate to shorten some things makes sense. I don't think they meant for us to do it though, because both of these you should be able to just plug directly in the CAS and get the value. So yeah, why not? Let's practice doing it by hand. Okay, so we have y equals x natural log x. Product rule means we have to do what? What are some of the steps involved in product rule?
Would you define each of the sections of the equation as u and v,
That's
and
exactly right.
then the derivative of each of those parts?
Precisely, yeah. So it doesn't matter which order you do them in, u and v. Product rule is quite forgiving in what you define as which, so long as you have them separated, that's all that matters. And then of course, yes, getting the derivatives of each of these. All these are fairly straightforward derivatives, you find them on your formula sheet. The product rule itself is also on your formula sheet. From there, it's a matter of just subbing into the product rule, which ends up being what's effectively a cross multiplication. You multiply along the diagonals and add the results together. So you're going to have x over x, because it's x times 1 over x. So when you do your dy dx, you're now going to have 1 for that, and then 1 times natural log x gives you natural log x. That's pretty much it. So we have our derivative. Let me just double check that. X natural log x, diff. Yeah, okay. I was actually expecting natural log x plus x. I don't know why. Anyway, this is correct. Now, second part of it, hence find the value of the integral from 1 to e of natural log. So we gotta now find this. The reason why it says hence find is because we can't just anti-diff this ourselves using our using any like formula on our formula sheet, because we don't actually have the anti-diff of the log. We have the diff of the log. Diff of log goes to 1 over x, anti-diff of log goes to something different. Which, for those who were here yesterday, we actually do kind of know what the anti-diff of log is, but it's not one you're supposed to necessarily memorize. So the reason it says hence find is because the previous information that we've just calculated will be relevant for doing this. How might we start putting things together? We did it.
If the derivative of the y equals x is log ex, and then we need to integrate log ex, would it just go back to the x multiplied by the natural log of x.
Yeah,
Like
so
it'll just go back to the original equation.
that's precisely right. If you integrate the derivative, you get back to the original. That's something that's true of all functions. And because we have this derivative and original function relationship, then yes, one of the things we can do is integrate both sides of that equation. And what we'll end up with is essentially, in fact, maybe to make it a bit clearer, rather than using specifically dy dx, I'll use ddx notation, and it's specifically of this function, x natural log x. The derivative of that is equal to 1 plus natural log x from there. And what you're suggesting, which is correct, is when I integrate one side and integrate the other side, I should basically cancel out, getting us back to this. So what that means is you're now going to have x natural log x is equal to the integral of 1 plus natural log x dx, which is quite nice because we're trying to find this one, and what we have over here is very, very similar. We just got to rearrange it ever so slightly. How do we now make that more like the integral we need to find?
Would you like split the integral?
Split the integral is absolutely correct. Yeah, whenever you have a plus or a minus separating two functions, constants count as well. You can split that integral. So we're going to have the integral of 1 dx plus the integral of natural log dx. Whoops, probably should say natural log x on that. Natural log x dx. We have now split the integral. We now have just the antidiff of log more or less on its own, or at least very close to being on its own. Still x natural log x over here. So the only thing we would do to get it on its own would be just subtracting this remaining term. X natural log x minus the antidiff of 1 is now equal to antidiff natural log x. So that's practically like the bulk of what we have to do and identify. The rest of this just becomes a matter of simplifying what we have and applying it to the question we're trying to solve, which is getting all the way to the definite integral, not just the indefinite integral. So when it comes to simplifying or further substituting to solve what we need, what further needs to be done?
Well, you know the integral of 1 is just x, and you can like sub it in.
Yep, nice and easy. We've done our integral of 1. That is also equal to integral natural log x dx. And then when you say sub in, did you mean just replacing this, or did you mean something about subbing these in?
I don't really know, to be honest.
Sure, fair enough. But yes, so definitely doing that antidiff for sure. So this is what we've effectively achieved here is the antidiff of log x natural log x take x. Right? If you have this statement here, this means the antidiff of natural log. So when you have an equal sign, it means that this is that. So when you think about when you're doing a definite integral, there's two parts to it. One is you need to antidiff what you have, and the other is you need to sub in the boundaries, which is e and 1. We've done that first part here. This is, for all intents and purposes, your capital F of x, your antidiff. So, to bring it home, we now know the antidiff of this. How do we then finish this definite integral off?
So sorry, can you repeat the question?
Yeah, so basically we're trying to now finish off this definite integral. There's two parts to it. One is getting the antidiff, which we just did here. And the second part of any definite integral is to sub in the terminals. So I'm curious to hear what that looks like. Anyone know what our next line of working would look like? That's alright. So it would just be subbing in the terminals. So for definite integrals, the equation for it is always capital F of top minus capital F of bottom, where capital F is the antidiff of whatever function you are trying to do the definite integral of. So if we already have our antidiff, capital F of x here, we're now just doing exactly this, capital F of e minus capital F of 1. Which in this case is going to be e natural log e minus e, and that'll be the first one, that'll be capital F of e minus capital F of 1. So 1 natural log 1, try to put this in brackets to be clearer, minus 1. Once we simplify this, that'll be our final answer. These have specific like easy substitutions, solutions to them. Natural log of e, does anyone remember what that simplifies down to? Alternatively, natural log of 1, that also simplifies down to something as well. Anyone
Would
remember?
natural log of e become 1 and natural log of 1 become 0?
Exactly right. Yep, those are our logarithm identities, and that'll make the final solution of this much simpler. So you're going to have e minus e, which of course is going to cancel, and then you're subtracting, well, that goes to 0, so subtracting minus 1 becomes plus 1, so final answer is 1. So when we give our final answer, just to be clear, because the steps do kind of get a bit messy, it's said solve this, so when we give our answer, we're going to repeat what that actually was, and then write what it actually equals, which is a nice neat answer at the very end. It's a very standard sequence of steps that we followed there. This is where you have a diff-antidiff relationship. You have derivative related information and you want to find a related integral. I have a whole guide with all the steps that you're supposed to follow outlined, and we've just done that here. If there's any questions about how that's worked, feel free to let me know and I will explain further. Otherwise, part B. This time we have a slightly different function, x natural log x, but that natural log is raised to a power that we don't really know what it is, just that it's a positive integer. Very similar question, still just find the diff. But the way we find that diff might be a bit tougher. So whenever we're doing a diff, one of the first things we want to do is figure out, am I using product rule, quotient rule, or chain rule for this thing? It's never going to be none of them, because otherwise the diff would be exceptionally easy and wouldn't appear in your exam.
Hey, I might be misreading the question. What does that say? That's integral E1, but then what's the
As in what I've written down, or what's on the...
yeah,
yeah,
what are
natural
you
log. So that's
Oh,
a
okay.
shorthand for log ex. Yeah, that's meant to be 1 to e of natural log dx.
Right, thank you.
Yeah, no worries. But yeah, as for the part B one, x natural log x to the power of n, that's still going to be a product rule because it's x times a function, where that other function would be natural log of x to the nth power. So, just like before, we're going to start out with a product rule. So let's write it out. We have y equals x natural log x, but that natural log is the power of n. And so once again, we're defining each of our terms. V equals natural log x power of n. The challenge here now is going to be v dash. How do we do v dash?
Would you use chain rule?
This will be a chain rule, precisely. Yeah. So we'll just give this its own little section. As for how we use chain rule, do you want to walk us through how we might use chain rule in this case?
Yeah, I started by bringing down the n and multiplying it by the derivative of log ex, so it becomes n on x,
Mhm.
and then multiplied by the log e of x, but then that's now to the power of n minus 1.
It's actually perfect, yeah. Did you do that all in one line, or did you have further working out there?
I did that all in one line.
Yeah, sick. That's really good. Because yeah, what you've basically identified there is the chain rule itself. Dy dx is equal to du dx multiplied by dy du. So what is it? This bit here is dy du. This bit here is dy dx, I think, if I'm pointing those out correctly. And yeah, it's really cool you're able to do that all in one go there. I'll break down these steps a bit further, just in case anyone was lost on what's fully going on there. So the way you do any chain rule, broadly speaking, is you figure out what substitution would bring your function to a basic function. Natural log to the power of n is not a basic function, but if I do a substitution u equals natural log x, then when I write out my new function in terms of u, I now just have u to the power of n, which is a basic power function. So I then do my diff of each of those, n u to the power of n minus 1. That's the du dx bit. Oh, excuse me, no, it's the y du bit there. And then u dash would be the du dx, which is 1 on x. And all we're doing is multiplying those two things together. That's why you have the n and 1 on x being multiplied, and you have the u to the power of n minus 1, which is this thing, because u is natural log x. So to show that in a bit more detail, you have 1 on x multiplied by n u n minus 1. That gives you the n on x, and then all you do is replace the u with natural log, because that's what it was, thus getting us what we wanted. Nice. Then from here, we're now going to continue that product rule. If there's any questions about the sequence of that, by the way, let me know, and I'll explain that further. But for now, we're going to have our final dy dx is, so that's just natural log x power of n plus this cross product, so it's going to be x times, well, those are just going to cancel then. X times n over x just gives you the n, and then natural log x power of n minus 1. Again, just copying down from there. Let's get rid of this so it's a bit nicer. Cool. That's an answer. You can leave it like that. There's also a bit of factorizing you could do, should you wish. Noticing that both have natural log x power of something in there, you can factorize things further. The term you would want to factorize in this case, where do I have this? Oh, yeah, that's part of this bracket. Yeah, the term you'd want to factorize in this case would be the n minus 1 power there. Should you want to, of course. That's going to be ln x power of n minus 1, and another set of brackets, one copy of natural log x would be left over, and then just the coefficient of this one would be left over. Probably going to set us up for a question down the road, but as far as when you leave your answer for this particular question, either of those are going to be fine. Cool. Okay. That's part B done. Part C. Let I sub...
Why, wait, sorry, for the second part of that, why is it plus n rather than multiplied by n?
Y plus n rather than multiplied by n. So what I've done via factorization is take this whole thing out as a common factor. So this bit, if I take it out as common factor, leaves just the coefficient n left over. And this bit, when I take this out, just leaves a natural log. And so what you're seeing is this term comes from here, this term comes from here. Because I've taken this whole thing out as a common factor. Maybe to make it clearer, if you had like n was 3 here, then that would make n as 2. Oops, n as 2 there. And so when I take out common factors, I would take out power of 2 at the most, leaving a power of 1 here and a power of 0 there. So
okay, that makes sense. Thank you.
Yeah, cool. get rid of all that. Okay. Part C. So I sub n is equal to the integral of something we've seen kind of similar before. For n greater than 1, show that I sub n is equal to I sub n plus n I sub n minus 1 equals e. Sure, okay. So subscripts isn't something that shows up a whole lot in methods. The subscript of n is essentially another copy of our power in the function. So for instance, I sub 3 would just mean you have n is 3. So when we now read this sort of thing, if n was 3, you'd now have I sub 3 times I sub 2. And by sub I mean subscript. So in other words, proving this identity for a specific value, let's say, if you had n was 3, what you would do is you would solve this for n equals 3, you would then also solve that for n equals 2, and then prove that the addition of those two things in this equation add up to e. That's how you do it for a single value. We're trying to do it for all possible n, which is fantastic. That's the idea of what's going on there. The subscripts of those is relevant to the power itself. And we can kind of already see it. If we have a look at the answer we just got, we had power of n and power of n minus 1 with that coefficient of n. It's a very similar setup to what was shown in the book itself, where we had in and then n times with n to the minus 1 as a thing on the next bit. So already we have something that's very, very related. The question now becomes, how are we going to now prove that that statement holds for all n in that particular equation there? Furthermore, this is an integral relationship, not a diff one. We've done the diff right now. We need to do the integral. So it's a bit different. It is still basically the same question as 8a, which was evaluating that anti-diff. This one now just has a power of n attached to it, but the steps are going to be largely the same here. So let's see what that's going to end up being. So once again, you want to anti-diff both sides of your equation. So now that I'm looking at it, I guess doing this was kind of irrelevant because that makes the anti-diff much harder. You'd rather have the separation of the terms there instead. So anti-diffing both sides of that equation means the left-hand side goes back to y, which was x natural log x power of n. So x natural log x power of n, and it's going to be equal to the integral of natural log x power of n dx, and I might as well just split it up already, plus the integral of n times natural log x power of n minus 1 dx. The one that we are trying to find is 1 to e of natural log x power of n. That's the one that we want. So if we look at what we have, that's going to be that one there. So we just got to get that one on its own, which is going to be a matter of essentially just subtracting this one over here. Oop, hang on, question. Send these notes after class. The handwritten bit, yeah, I could do that. I could export this. It's a bit challenging because I also have all the notes from every other class that's in here. So I guess just scroll to the bottom of the thing and you'll see these ones here. That, and they're part of the recording, of course, so you'll be able to watch them there. Yeah, that's fine. Okay, where were we? So we're trying to get this one on its own, which means subtracting this integral. Oh, another question. insanely long for. Yeah, it's a very long one. I use the same thing. You guys have seen it before, where I'll start trying to write on the screen and it won't write anymore, and that's simply because I've maxed out the document, vertically speaking. So I make a new one. But yes. So okay, right. So we're gonna have x natural log x power of n, and then subtracting that integral. Integral n natural log x power of n minus 1 dx is equal to, oh that's right, before I forget, because we have a few newcomers, I was looking at the like exam reports for certain questions when we were going through past VCAR exams. They really care that you put dx in these integrals. So I am trying to be a bit more specific about putting dx's on all of those. It's pretty easy to be lazy about that sort of thing, but I've seen in the exam reports by VCAR that they really care about you putting dx on these things. So just thought I'd mention that. Make sure you do it for yourself. But okay, that one's going to equal integral natural log x power of n, which therefore has got us our capital F of x. I have zoomed out too far. This is bad. This is our capital F of x. So far, these have been the exact same steps. It's just a much more complicated looking function. We had our diff function. We just integrated both sides and then looked for the integral that we wanted out of that. From here, can we evaluate that? Let's see. Well, we can definitely take the n out. N's a coefficient. So we have n integral natural log x and take 1. But can we actually evaluate that? Do we have anything to help? So if I want to know what that anti-diffs to, do we have something from a previous set of working that can help? Not particularly there. We have the diff. What did we do before? We did something with this. That was substituting in, but where's the bit? That's this bit here. ddx equals that. But we're already integrating both sides. How are we going to sub anything into this? Because ultimately we want to go, again, capital F of E minus capital F of 1, which means shoving E's into each of, not that, each of these spots, but because this is itself an anti-diff, I guess you can do E and 1 there as well. What to do? Let's try it. So capital F of E, gonna have E natural log E power of n minus, nah, it's not gonna work. We need to know what this antidiff is. Is this a time for integration by substitution? Perhaps, but I don't know if that's necessarily required. I'm going to take a peek at the answers just in case, because I do have a seeking suspicion that Integration by substitution could do it. Seems like it could do it by replacing natural log with u. But that's not specifically methods. So before resorting to that, I'm just going to suss this out. What did they do? Okay, part B using product rule. In that. Maybe what I'll do is I'll pull up the solution doc that I'm having a look at so you guys can see what I'm looking at. Okay, so I'm looking here for the part C bit. Now they say from this. What are they referencing? I don't see that symbol anywhere. Oh. Oh, that's kind of cool, actually. They're doing essentially the reverse of what we were. Oh yeah, Taihan, sorry, I just saw you had a hand up.
Yeah, I was just wondering if you could share like this document you had for the work solutions.
This one that you're looking at now on the screen share.
Yep.
This is the answer sheet. Yeah, this is like it comes with the textbook.
Oh, okay. Yeah, okay.
Yeah, I'll put it in there anyway. If it might be too big. Let's see. Is that going to be too big? Let's find out. Nah, looks like I'll be alright. Yeah, what they were doing here was kind of like the reverse of how we split the integral. They actually just combined the integrals, and that works even if it's definite. Right, so basically if I sub n integral was that, then I sub n minus 1 would just be the same, but replacing n with n minus 1. So if you now want to prove the this thing here, you can now just combine those together, and that does look like the diff that we had. So when you anti-diff back, you get back to what you had. That's pretty sick, actually. So let me revert the screen share, and then we'll do that. Is that good? Yes. Okay. So rather than us going through and doing all this, what they essentially intended, they gave us the integral to work with. They gave us I sub n is equal to e1 natural log x power of n, and therefore I sub n minus 1 is the same thing, but with n minus 1 on top, again with those dx's. So when you're trying to prove that I sub n plus n I sub n minus 1 is equal to e, it's a matter of now plugging both of those in and just combining those integrals together. So you now have 1 to e of this one, so natural log x power of n, and it's plus n times the natural log, this one, natural log x and take 1 dx. And if we look at what was created there, it's the exact same thing as our diff. Alright, natural log x and take 1, oh sorry, this one, that's the factorized version. Natural log x power of n and n natural log x n take 1. It's the exact same sequence. So when you do your definite integral capital F of x, you should get back to the original, which was this. Funky. So capital F of x is therefore x natural log, what was it? X natural log x n take 1. Oh, n, just n. Let me double check that. Cool. Okay. So I was right idea but wrong execution. Right idea in the sense that you want to be using the diff-anti-diff relationship, but I was then going at it from an earlier point rather than just using the equations that were already given to us. From here, the rest of it becomes quite easy. Capital F of E minus capital F1, you're just shoving E and 1 into both of these. There was a question that popped up, so let me quickly check that. Don't mind asking, when do we start a probability? You've already started that in school. Yeah, look, we can start doing more probability stuff if you like. Have you? Yeah, because I don't think... Has everyone done their integration stack yet? I think it's the first couple of weeks of term 3.
I have mine week 4.
Week 4, okay. Maybe in class 2 what we can start doing is looking at some probability stuff, and if there's specific questions that you guys want to have a look at for integration, submit those, and then class 3 we can use as still primarily integration focused, unless again other review related stuff. Maybe that's how we could do it, so we still get a bit of a head start on the probability stuff because you guys are still now learning that, but ultimately the stack that's coming up for you guys is the integration stack. That might be how we do it then. But yeah, anyway, so let's plug these in. Capital F of E is going to be E natural log E power of n, and that's it. So minusing capital F of 1 is going to be 1 natural log 1 power of n. Natural log of E is just 1, so 1 power of n is also just 1. So final answer E, and then natural log 1 is 0, so just E, which was what we wanted. We wanted to prove that when I add those two together, I get E, and we did. So when you give your final answer, you'd write it exactly as they wrote it, which is I sub n plus n I sub n take 1 is therefore equal to E. So we did a bit of a messing around there, so maybe it's a good idea to recap what we actually did. So part C, it says let I sub n equal that definite integral, show that some other stuff with the I n and I to n take 1. What should have been done off rip was, we already know what I sub n is. What we need to do now is figure out our I sub n minus 1, which, as I was saying at the very beginning of the question, just means replacing n with n minus 1. So we set up those integrals accordingly, which was this bit on our handwritten notes. From there, we're just going to plug those into the equation that we were told to plug them into, the one that's supposed to equal E, which is this one here. So we plug them in, condense the integrals down into each other, because that works both ways. You can split them up and you can combine them into each other, and then just evaluate from there using, once again, the integration by recognition, noticing that the function in our integral is itself the diff. So when you anti-diff the diff, you get back to the original, which we happen to know, which I have printed in the red capital F of x. Then from there, the rest is kind of whatever. Plug in your e's, plug in your 1's, and you sort it. So that was a bit of a mess, but are there any questions after that? If not, like, part D is kind of whatever. It's essentially just saying if n was 3, what do we get? We've already kind of done this for a question. We were showing that you can plug in just the value and then see what happens afterwards. Do we want to go through part D or a new question? I don't think that's going to be much different. let's do another one then. Question 9. Okay, what have we got here? We got two quadratics. One is pointing upwards, the other's pointing to the right. A and B are positive, intersect at the origin. Makes sense for quadratics, or I guess parabolas I should say. And at the point RS, find that other point they intersect. Prove two curves divide. Jesus, okay. Let's just start the first bit there, which is find R and S in terms of A and B. R and S are the x and y coordinate respectively of the point that they would intersect. So to get an idea of what we're looking at here, we can draw a rough graph of what these functions might be. So if we rearrange into more readable functions, the graph of y squared equals ax becomes y equals plus minus root ax. And the graph of x squared equals by just becomes, maybe we'll call this one y1 and this one y2. That will therefore become x squared over b. So one of them, clearly a quadratic. We'll call that y2. And the other is a plus minus root. And because this is positive, we know that a and b are positive. That's why we're pretty confident that they're going to start up and right rather than down and left. So looking at what we have, it makes sense why they would now intersect at the origin, and we can identify another intersection point. That is the point RS that we're trying to find there. That's the point RS. So now that we have both of those drawn out, things should be a bit more clearer how you might go about it. Any suggestions how we're going to find R and S? So what's the intersection between two functions? That's always solved the same way, regardless of what the functions are. Could be two straight lines, could be a quadratic and a linear, could be anything. Any intersection point between two curves is just done by equating the curves together. Equation 1 equals equation 2. That's because they share a y and an x at that spot, so you can replace the y of one with the y of the other. Problem with this case, at the very least, is just drawing an equal sign between these two things is not super doable, because one of them's a relation, it's got a plus minus in there, the other's a function. So we're going to have to do a bit of simplification on that plus minus root to get something a bit more usable. What might be done? Only one of, oops, almost gave too much away I think. Yeah, we don't need a plus minus there. Not all of that information is relevant. If you look at the picture of the graph that we have, what could we further simplify that plus minus root into? What I've drawn there are two separate functions. One of those is the basic square root x, the other is the negative square root x. If you combine the two, you get that sideways parabola. So, if we look at where our intersection is, it's in that quadrant 1, and it only exists on the positive part of the root. So when it comes to equating our two equations together, we're only going to take the positive part of that root. So we're going to do exactly that. Root ax is equal to x squared over b. We're going to take the positive version rather than the negative because that's the one that actually has the intersection. From here, we solve this more or less however you'd like to. Probably going to start by squaring both sides, killing the root. That's going to give you x4 b squared. Get the x's together, so ax take 1 on b squared x4 equals 0. Try to resist the urge to divide both sides by x. That will kill out one of your solutions, that solution being x equals 0. Not that we particularly care in this case, because we're not trying to find the origin solution, we're trying to find the one that's further up. The x equals 0 solution would give you that bit. But good practice is to do a factorizing approach instead. Take common factor of x out the front. You now have a take 1 on b squared x cubed equals 0, thus getting you x equals 0, and a equals 1 on b squared x cubed. Yeah, and then continuing on. So a b squared equals x cubed, x equals cube root ab squared. This is the one that we care about. This is the other solution, your origin. That's our x coordinate, which therefore makes this r. R equals the cube root of ab squared. That's this bit here. We also need the y coordinate. Can anyone tell me, now that we have r, how might we get s, the y coordinate? So any xy pair that exists on a function simply just means if I shove in an x coordinate and simplify things, what I get is a y coordinate out of it. That's what any function means fundamentally. So if we know that our x is cube root of ab squared, to get the corresponding y, we chuck that into either of those functions, y1 or y2. Any of them will work because it's shared on both of those functions. So just choose the easiest one, which in this case will be the quadratic. Roots are a bit of a pain to work with. So y2 is x squared on b. So what I now do, y2 of r, which is that bit there, that is going to end up being my s, which is now going to be, so instead of x squared, I now have, I now have the cubed root of ab squared, and that itself is squared, because I'm replacing the x with that whole value, and then over b. I was fine to leave this with the cube root and the square on the inside there. It's getting a bit messy with s now. I'd probably start considering using index notation for this sort of thing as well now. So in other words, converting all those into their relevant indexes. So you'd now have the cube root just means power of a third. So you have ab squared power of a third, and then that is being raised to power of 2. And then maybe instead of having the denominator of b, we now have b to the minus 1. From here, condense everything down. So you have ab squared, the third times 2 for 2/3, b to the minus 1, and continue on. Because if you're already doing this, to simplify what this looks like, you might as well go all the way and distribute all the way through. A to the power of 2/3, b to the power of 4/3, minus 1 gets us to a third. Just double checking that again. 4/3 minus 3/3, yes, positive 1/3. That'd be the neatest way of writing that one. We have s, we have r. Any questions there? I think it's been a while since we looked at our indexes. Cool. Alright, that was the quote easy part of it, which is just finding the intersection points and maybe doing a bit of simplification math there. Next part. Prove that the two curves divide the rectangle given by those coordinates into 3 regions of equal area. So the two curves that they're referring to are what I've denoted as y1, y2. That's the two parabola shapes. Divide a rectangle with corners 0, 0. So that's going to be, hang on, question. Go to the bathroom. Oh, yeah, you can, do whatever. It's going to be recorded, so you can catch up on it when you get back. Okay, so each of those coordinates, so we mentioned 0, 0, so that's going to be one part of our rectangle. It said 0s, so that's going to be from here to here. R and S, which is going to be that one, and I think it's a pretty safe assumption to say this is the next one, R and 0. Yeah, okay. So those are the 4 coordinates that are mentioned. The question is asking us to prove that this rectangle that was created is divided into 3 regions of equal area. Yeah, okay. Well, I can definitely think of one way to do that, which is just find each of them individually. That's kind of interesting, because there's A's and B's in it, and A and the B aren't necessarily related to each other. Like, A could be a massive number and B could just be 1, and yet, despite that all, it seems to be the case that we can prove that the regions that are created are still equally split. I guess that makes sense, because when you widen one of these, like let's say I'm widening this parabola, all that means is it just shifts where you have this. The intersection point is now here, and so your rectangle now becomes this. And so now looking at the next little rectangle that you could have created, yeah, I guess visually speaking it does kind of make a bit of sense why it's going to now split into thirds. Problem is proving it. So I can definitely think of one way to do it, which is going to be a lot of definite integrals. I was thinking maybe there could be something kind of like how we do, what is it? Like the inverse integrals, where instead of doing integrals for each individual shape, you just do, you make use of the line y equals x, but because A and B aren't necessarily like in sync with each other, they don't have the same coefficient or comparative coefficients, these are not inverse relationships. I've just drawn them to look sort of like that way. So we can't rely on that, which means I guess the only thing we're going to do here is our definite integral solution. So there's 3 separate regions. There is region in the middle, there's this region, and there's this region. If we find each of those individually and prove that they end up being the same number, then we have proven it. Do we want to do that? Probably not. So is there a better way of doing it? I'll at least talk out loud as to what you would do if you had to do each of those 3. Area 1 is going to be a sort of top take bottom scenario where you use this roof, the line y equals s, as your top function, and you use the square root curve as your bottom bit, and so you essentially do the integral from 0 to r of the top bit minus the bottom bit. For the one in the middle, you would just do a simple top take bottom with the 2 functions themselves, the root on top of the quadratic, and then lastly, for this bit here, you would do the quadratic on top, and that would be it actually, just a quadratic from 0 to r. Then you would compare the 3, see how that goes. That's a lot of writing, so I'm going to try and think and see if there's a better way of doing that. Maybe, can we split this thing down the middle? Probably not. What else could we do? Well, hang on, this is tech active. Maybe that's what they were. Maybe we're supposed to rely on that. Yeah, no, what am I saying? It's tech active. Let me see, is that what they did? Yeah, that's exactly what they did. Okay, yeah, no worries. We'll just use our CAS. I got into the habit of writing everything by hand that I forgot that we actually do, or are allowed to use our CAS for some of these. Okay, so let's do exactly that. So all of our functions, we had, let's call this one h of x. That's going to be the root ax. A times x. For those guys who are new to my classes, I stress a lot about making sure you put multiplications between your variables. The reason why is because if you don't, it'll have ax as its own variable. So when you try to use it for other things, it won't count them as two separate things, a and x. It'll count them as the same thing. So make sure you are deliberately putting multiplications between those things. And we'll have our other function as x squared over b. Cool. Okay. Question. Zoned out for a bit. We're trying to find the three areas. Yes, trying to find the three areas. I was sort of debating whether or not we should do all the working for it, and then I realized this is a tech active thing. We can actually use a CAS for this. All you would have to do is write out your integrals when you're doing this on your exam, let's say, or your SAC, and then use the CAS to actually evaluate what those are. So let's do exactly that. So as I mentioned, this top bit here would have the line y equals s as your top and the root as your bottom. So we'll do exactly that. So we're doing it from 0 to the intersection point, which is r, which, just bear with me while I copy that down. What was our r? Our r was the cube root of, actually before I do this then, maybe I'll define it. R equals the cube root, that's not the cube root, this is cube root of a times b squared. Yep, the other one was s, we'll define that. S was a to the power of 2/3 times b to the power of a third. Oh wow, that was really off center. Sorry guys. Okay, now continuing on with what we said, we're doing it from 0 to r, and it was the top, which is s, the line y equals s. Take the bottom, which was the root. Which one was the root again? Root was h. That's going to get us that one. Nice. Next up, we've just done the top little bit there. Now we're going to do the middle little bit here, which has the root over the quadratic over the exact same domain. So let's do that. Root was h, quadratic was I. Those, are those the same thing? B over 3 as opposed to regular B. Okay, let's keep going. Next one, oh yeah, anyhow. Oh, that was just written. We can find the area bound by the graphs and subtract the squares. Yeah, find the area bound by the graphs, subtract the squares, area divided by 2. Yeah, okay, that will get you the other areas, yeah. That's fair. Finding that, finding the squares area, and then halving it. Well, yeah. Yeah, that would work. Because what you're doing is you're finding the full square, you're finding the middle bit, subtracting that out, and then, yeah, that'd be better actually. But I guess we're already here, so I might as well finish off what we're already doing. This one's the quadratic, so that's just the regular old I of x. Why do they all give 3 separate different looking things? That's not great. Like, that's what it's supposed to say. Oh, wait, I know why it's giving the modulus. It's because this. That's behaving weirdly in the CAS. They were all supposed to say this one here, AB on 3. That's what it had in the answer. So, let's see, is there anything we can do to show what's going on there? Yeah, if you look at what's happening here, the reason why you're getting this modular sort of thing going on is because it's, I think, trying to track both the positive and negative root. If you just treat them as positive, you'll see that b to the third and b to the 2/3 just condense down to b to the power of 1, and then that would be subtracted off of that. So the b's get cancelled down, leaving you with just the a bit there, the ab over 3. Similar with the other bit. So that's what was supposed to be happening there. I guess the CAS are just playing weird. The if you have a look at the solution set, it's a bit ambiguous how they got their answers there. I'm assuming they were just sort of rationalizing what the CAS was showing. So if we have a look again, you see the areas of each of those come out to be AB on 3, AB on 3. All 3 regions have AB on 3, therefore they're all equally distributed. Weird. Anyway, so this is part of the challenge of using the CAS. Sometimes you do have to try and work out what it's trying to do and where there might be some issues. Because what it's giving is a technically correct answer. It's just that we only care about a certain portion of the answer for our purposes. But okay, that's hit time there. Got through a decent number of questions. Tough ones, for sure. Were there any further clarifications I should talk about? If not, I appreciate you all for coming.
Thank you. Have a nice night.
Thank you. You too.
Thank
Thank
you so
you.
much. Have a good one.
Thanks, guys.
Thank you.
No worries. Thank you. Yeah, cheers. You too. How's it going, mate? Any clarifications? AFK? If you're on mute, by the way, you're on mute. Okay, maybe message me after class then if you had any questions. Or just pop something quick in the chat. Okay, maybe later. Take care.